In 2019, telescopes around the world captured something previously thought impossible: the glowing silhouette of a supermassive black hole. That image, along with the GPS in your phone and the detection of gravitational waves, all originate from the mind of a single person. Born in Ulm, Germany in 1879, Albert Einstein grew up in a home defined by two very different disciplines. His father was an engineer who built electrical equipment, and his mother was a talented pianist. When Albert was 5 years old, his father showed him a simple pocket compass. To the young boy, the way the needle independently snapped to point north was transfixing. He realized there was an invisible force acting on the object across empty space. He later recalled that this compass gave him a profound realization: something deeply hidden had to be behind things. This sparked a lifelong conviction that the universe is governed by an elegant, harmonious order. That search for hidden harmony would define his entire career. It would lead him to challenge the most basic assumptions of the scientific world, beginning with how we understand light and motion. Einstein was a brilliant child, teaching himself Euclidean geometry over a single summer. But he openly despised the rigid, authoritarian schools of late 19th century Germany. He rejected mechanical memorization in favor of deep, independent questioning. This rebellion had consequences. When he first applied to the Swiss Federal Polytechnic School in Zurich, his exceptional math and physics scores weren't enough to secure admission. He failed the entrance exam because he struggled with French and botany. This diagram represents a thought experiment he posed to himself after transferring to a more progressive school in Aarau, Switzerland. What would it actually look like to ride alongside a beam of light? Even after eventually gaining admission to the Polytechnic and graduating, his habit of challenging his professors left him without recommendations for university jobs. For 2 years, he scraped by as a tutor before accepting a low-level position reviewing patent applications in Bern. Working in isolation, far from the pressure of academic dogma, Einstein spent his free hours questioning the most basic mechanics of the physical world. He wasn't restricted by what was supposed to be possible. He was only limited by his own imagination. In 1905, at 26 years old, the unknown patent clerk published 4 landmark papers in a prestigious physics journal. The first proposed that light is composed of discrete packets of energy, laying the groundwork for quantum theory. The second provided the mathematical proof for the random movement of suspended particles, confirming that atoms and molecules physically exist. Then came his special theory of relativity. He argued that the speed of light is entirely constant, but the dimensions of space and time are relative, stretching and compressing depending on the observer's motion. As this animation illustrates, a brief follow-up paper introduced a simple equation: E equals mc squared. This formula revealed that mass and energy are entirely interchangeable, and that an almost incomprehensible amount of energy is locked inside even the tiniest speck of mass. In a single year, he had rewritten the accepted rules of light, matter, and time. But special relativity only applied to objects moving at constant speeds. To truly understand the universe, Einstein knew he needed a theory that could explain acceleration and gravity. For the next 10 years, he engaged in the most exhausting intellectual struggle of his life. He had to learn entirely new, highly complex forms of non-Euclidean geometry just to build the mathematical framework for his vision. This model illustrates the core of his 1915 general theory of relativity. He proposed that gravity is not an invisible force pulling objects across empty space. Instead, the presence of mass causes the very fabric of space-time to curve. When planets or stars move near a massive object, they aren't being tugged. They simply orbit along the natural geometry of those deep curves in the fabric. This elegant math remained purely theoretical until a 1919 total solar eclipse. An expedition led by British astronomer Arthur Eddington measured starlight passing near the sun. Exactly as Einstein predicted, the sun's immense gravity physically bent the light from the stars. The physical proof of this hidden cosmic order was splashed across newspapers globally. The isolated patent clerk from Bern was thrust into the spotlight, becoming the most famous scientist on Earth overnight. But his fame could not protect him from the political realities of Europe. In 1933, as Adolf Hitler seized power, the Nazis targeted Einstein, burning his books and denouncing his research. Realizing the danger, he fled to the United States and never returned to Germany. By 1939, Einstein and his fellow physicists realized that the new regime might weaponize scientific advancements. He co-signed a letter to President Franklin Roosevelt, explicitly warning that Germany was capable of constructing extremely powerful bombs of a new type. Because of his outspoken pacifism, the U.S. government considered him a security risk and kept him entirely separated from the Manhattan Project. Yet, the theoretical foundation for the weapons they developed was his own mass energy equivalence equation. When the atomic bombs detonated over Hiroshima and Nagasaki in 1945, incinerating hundreds of thousands of lives, Einstein was devastated. The destructive potential of his mass energy equation had been proven on a massive scale. Horrified by the outcome of his intellectual pursuits, he spent the rest of his life using his global influence to aggressively advocate for nuclear disarmament and international peace. As he advocated for political harmony, the scientific community he helped build was moving in a direction he deeply opposed. The field of physics was increasingly dominated by quantum mechanics, a discipline defined by probability and chaotic subatomic behavior. Einstein firmly rejected the idea that reality was inherently random. He believed strongly in a deterministic universe, where cause directly leads to effect, summarizing his frustration with the phrase, "God does not play dice." This sparked a profound, decades-long debate with quantum pioneer Niels Bohr. Bohr, entirely comfortable with the probabilistic nature of the universe, famously replied that Einstein should stop telling God what to do. Einstein spent his final decades at Princeton working in relative isolation once again. Up until his death in 1955, he relentlessly pursued a unified field theory, a single mathematical framework he hoped would link gravity and electromagnetism, proving the ultimate order of nature. He died before he could find that final equation. He left behind the mathematics that describe the universe, alongside a legacy of activism that insisted science must serve the survival of humanity.